Good morning, everyone. My name is Lorenzo Corradi from University of Rome Tor Vergata. My presentation will focus on the optimization of the debinding and sintering process of stainless steel AISI 316L parts produced through fused filament fabrication. This work was carried out in collaboration with engineer Bragaglia, engineer Ceci, Professor Costanza, and Professor Tata. Additive manufacturing refers to a group of innovative technologies that build components layer by layer, starting from a digital 3D model. Compared to traditional manufacturing methods, it allows the production of very complex geometries, optimized and lightweight structures, and customized design with reduced material waste. Today, AM is increasingly used in several strategic sectors, such as aerospace or automotive, energy, and consumer production, where design flexibility and structural efficiency are essential. Additive manufacturing offers key advantages such as geometric freedom, component customization, reduced material waste, and high production flexibility. However, there are still important limitations. The mechanical property can be anisotropic, dimensions are limited, and the process repeatability is not always guaranteed. These aspects become even more critical with metal FFF, where the final component quality strongly depends on the post-processing stage too. Here we can see the full manufacturing process for metal FFF. First, the metallic powder is mixed with a polymeric binder and then pelletized to produce a feedstock. The feedstock is extruded into a filament, which is used during 3D printing to obtain the so-called green parts, still rich in binder. The printed parts then undergo debinding to remove the organic phase and sintering to densify the metal structure and obtain the final components. The objective of this study are three. First, the fabrication of AISI 316L disc specimens using FFF technology. Second, the analysis of the debinding and sintering stage through TGA and FTER to evaluate the removal of the polymeric binder. And third, the microstructural characterization of the final parts after sintering using SEM and EDS. The goal is to understand how these post-processing steps influence the final quality of FFF 316L components. Here you can see the first steps of our manufacturing process. We started by designing the geometry of the disc specimen using CAD software. This model was then printed and the results is the so-called green part, which still contains a significant amount of polymer binder. So it's not metallic yet and requires future processing. After printing, the parts still contain a lot of polymer binder, so the first step is chemical debinding, where the green parts are dipped in nitric acid to remove the binder and prepare the structure for sintering. Then we apply a two-step sintering cycle. A first thermal debinding at 600 degrees C, and then sintering at 1380 degrees C, under reducing atmosphere to densify the metal. For the chemical debinding, we tested different immersion time in nitric acid. The most effective conduction was 40 milliliter of distilled water and 8 milliliter of HNO3 at 120 degrees C for 25 minutes. Here we can see the green specimen before the treatment and the immersion step, and the appearance of the part after the binding. Once we identified the optimal condition, we compared the sample treated for 5, 25, and 30 minutes using FTER and TGA against the untreated specimen. The TGA curves show that chemical debinding removes part of the polymeric binder, already reducing the mass loss during aging. This partial removal generates internal channels, which will facilitate the evacuation of the remaining binder during thermal debinding. The residual degradation peak indicates that some reaction products are still present and will be eliminated in the following thermal step. The FTER spectra show that longer immersion times in nitric acid lead to a progressive reduced in the characteristic POM peaks, indicating the partial removal of the polymeric binder. At the same time, additional absorption bands appear associated with the residues formed during the chemical etching step. These results confirm that what was observed in the TGA analysis, so the chemical debinding facilities the later removal of the remaining binder during the thermal stage. Here you can see the microstructural observation of the sintered specimens. Inside each deposited layer, the metal powder appears to be properly densified. However, the interfaces between layers show significant porosity and a lack of bonding. This means that the densification during sintering was effective within the layer, but not sufficient between them, leading to anisotropy in the structure. This avoid are a clear identification that the debinding and sintering conditions still require optimization to improve interlayer diffusion. So, here we can analyze the surface morphology using SEM and EDS. From the SEM image, the surface appears irregular and partially oxidized, confirming what we observe in the microstructure. The EDS results show the expected metallic elements of 316L, iron, chromium, and nickel. However, we also detected a relatively high amount of oxygen and even some carbon residues. This indicated that oxygen occurred during sintering and the binding was not fully complete, leaving some organic contamination behind. We also performed the microvicars hardness test on the sintered specimens using a 500 gram load. The average hardness value we obtain is around 205 HV. Is consistent with the typical range reported from 316L stainless steel. This confirmed that despite the porosity observed, the local mechanical response of the material remains acceptable. To summarize the results of this work, the combination of chemical and thermal debinding proved effective in removing the POM binder, as confirmed by FTIR and TGA. However, the sintering step is extremely sensitive to the processing condition. Oxidation and microstructural inhomogeneities still occur in the current setup. The densification results clearly show that atmosphere and temperature control must be further optimized to achieve fully dense and defect-free parts. Overall, the study highlights that the critical interplay between the binding and sintering, where even small variations in the process can strongly affect the final quality of metal FFF components. So thank you very much for your attention. It has been a pleasure presenting this work.